Without further ado then, programming Granite by Nick here, please.
Hey, it's good to see you all. I'm Nick Rioux. I'm a PhD student at the University of Pennsylvania. I work with Steve Zdancewic, and I'm really excited to share some thoughts on language design that I've been working on lately in this language we're calling Granite. What is Granite? Granite is a programming language aimed at two things. One big thing it's aimed at is extensibility. So we should be able to write programs and extend them with new features without having to go back and change the old code. And another thing that it's aimed at is scalability. We should be able to design programs that run well on one processor and then scale them to multiple processors or even multiple machines across a network. So Granite is functional, it's declarative, and it's aimed at doing these things very well. It's really committed to sort of the core tenets of purely functional programming, which is where the name comes from, with reference to this Simon Peyton-Jones quote. Another thing about Granite is it's pretty minimal. So it really only adds one new language construct that programmers have to learn. And we'll dive right in and sort of take a look at what that is and what that means for programmers right now. So that one new operation we call join. It takes two programs, and it runs them both in parallel, and it then merges their results somehow. What exactly that merge is depends on the exact kind of data you're working with. It's overloaded. But the important thing is that join here forms a semilattice. So this operation is associative, it's commutative, and it's idempotent. And there's one more property that joins have, and that's that they're angelic. So the idea here is that a join should succeed as long as at least one of its inputs succeeded. So here bottom represents a failed or a divergent computation. And so if one side of a join succeeds and the other one crashes or runs forever, then the whole join should still succeed. And we also have, in addition to bottom, we have a sort of bottom of the values value, which is called undefined here. And it is not an error in of itself, but it's a value that if you try to use it in any interesting way will cause an error. So let's see what you can do with it. So we're going to write a function that you can't write in a sequential language that you can write in Granite, and that's the call by value parallel OR function here. So parallel OR is going to take two thunks that are expected to return Boolean values, and it should return true if either of the thunks return true, even if the other one fails. On the other hand, it should only return false if both of the thunks return false. So we're going to write this function in three cases. And each case is one of these pattern matching sort of single branch let expressions. So this is actually the same syntax as Haskell. The left-hand side of the equals here is a pattern that the right-hand side is expected to match. And the body of the let runs if the pattern does match. If the pattern doesn't match, you get bottom. So here, when x is forced and it returns true, then this whole branch returns true. And we can do that a couple more times. And we just say that when either x or y return true, the result will be true. And if both return false, then the whole function returns false. Great. So let's look at some other uses of joins. We have finite sets on Granite. And as you might expect, a join of two sets is just the union of the two sets. We also have this n-ary join construct, which is just an elimination form for finite sets. And you can here, the join will basically iterate over each of the elements of the first set in parallel and join together the body evaluated at each individual element of the first set. So we use the for in join notation here to mean these sort of big joins. Joins also work on records. So it behaves kind of like record concatenation, with the caveat that if you join two records that have shared fields, the join will sort of recursively distribute over those shared fields. So here we have two records. The first record has fields x and y, and the second has fields y and z. So in the output of this join, we get a field where the x and z components are sort of the same as the components that we got in the inputs, because there was only one x field and only one z field in the inputs. But in the y case, we had two inputs, so both sides of the join had a y component, and so we get the output y component by just joining the two input y components. Join doesn't always make sense. There are some things that you just don't want to join together. So joining true with false is one such case. And we raise runtime errors in these situations. We call them ambiguity errors, and we write ambiguity errors as top. Now, Granite is untyped, so we can't really prevent these from happening at runtime. It's up to the programmer. But we are encouraged that, we would like to have a type system in the future, and we're encouraged by recent results that sort of show how to avoid these kinds of, or how to rule out these kinds of errors statically. So the last kind of join that we haven't seen yet is a join of functions, and this is a neat one. So here we have two functions, and we join them together, and syntactically it doesn't really look like much. We just sort of distribute the join over the bodies of the functions. But semantically, there's something quite interesting happening here, which is that in the two original smaller functions, for example, in the first function here, when E1 makes a recursive call, its recursive call calls back to just that one function that contains E1. And likewise for E2. But in the joined function here, when either E1 or E2 makes a recursive call, it refers back to the entire joined function now. So this actually gives you a lot of power, and what it lets you do is extend recursive functions with new cases. So we can see that in the next slide, where this is kind of, you don't have to look at the details of this code, but the idea is that we're trying to sort of solve the untyped expression problem here. We have three evaluation functions, one for literals, one for addition, and one for multiplication. And each of those three functions only has one case. They each handle like one piece of syntax. And the idea here is that we can join these three evaluation functions together to get an evaluation function that works over all of the syntax, even when they're nested within each other. And so we end up with a function over one three-case data type that behaves exactly like we had just defined it that way from scratch. In Granite, we can go a little bit farther. We can actually use recursive functions to encode these sort of module-like structures that allow you to not only extend one function at a time, one recursive function at a time, but actually extend entire mutually recursive families of functions. All right, so that's it for compositionality for now. I want to move on to talking more about parallelism and also talking about how we evaluate Granite code. So this is kind of an interesting little Granite definition. So here we're defining a thunk named f, and when that thunk is run, it's going to return some kind of set. What else do we know about this, and what can we summarize? Well, this is a little bit weird because in a sequential language or a language like ML or something, you would expect this definition to diverge. And that's because we're making a recursive call back to ourselves at the same argument. So that seems like, a recipe for divergence. But it turns out bottom is not even a fixed point of this function. This function cannot diverge. And the reason is that we've said that the function must at least be a set containing the element 0. So bottom's not a fixed point, and there is actually a reasonable fixed point here. So let's talk about what this function is meant to do. The way to read this is to note that, first of all, the set that f is computing must include 0. And second of all, for every element I that is less than 9 that is in the set that f computes, then that set must also contain I plus 1. So you can read these two bullets at the bottom like sort of two inductive inference rules. And we should be able to compute the least fixed point here by sort of taking the closure over these rules. And it turns out, but how do we do that, like concretely? If we just try to design an evaluator like a normal functional programming language would have, like I said, we'll hit divergence. So something needs to change. And the answer is that there already is an answer out there. And the kind of evaluation you need to do is exactly the kind of evaluation that Datalog does. We need to sort of evaluate this thunk iteratively. And this has been done before. There are a few different languages that combine this sort of Datalog style semantics with functional programming. The most closely related is Datafun, which was introduced at my first ICFP in 2016. And it's a very closely related language. But one big thing that's new here is that we have general recursion and non-termination in our language, whereas Datalog was a total language. All right, so how does this actually work? Well, we're going to run f, this function that we were just looking at, iteratively. We'll run it basically a few different times. And we always start by saying at sort of the 0th iteration, f is going to return bottom. And then from there, we can, for each subsequent iteration, we run f. And the only thing that's unusual is that anytime we hit the sort of cyclic recursive call, we don't just naively recurse. Instead, we just look up the answer from the table, and we look at the last iteration. So so this definition says that formally. And the idea here is that iteration 0 is by fiat bottom, and iteration 1 is going to, in iteration 1, the right-hand side of the join is going to be bottom because f of 0 is bottom. And in iteration 2, we then will learn that 1 must also be in the set, and we're just going to keep repeating this. Turns out we'll repeat it to iteration 11, and then we'll have a set of the elements from 0 to 10, which is the least fixed point of the definition that we saw. So here's a slightly less contrived, sort of more interesting example. We can now write functions over cyclic graphs. So imagine that we have a directed graph. And we'll say that it's defined by some function neighbors, where neighbors takes the name of a node in the graph, and it returns all of the names of the nodes that are one hop away from the input. So from there, we'd like to define the reachability function, which gives you all of the nodes that are reachable from a certain starting point. And we define reaches of n1 to basically be the set that includes n1. That is, n1 is always reachable from itself. And it also includes everything that is reachable from any of the neighbors of n1. So once we've written this in Granite, we can go and we can evaluate it, and it works even for a cyclic graph like the one pictured here. And that's pretty cool because just naively translating this code to a language like Haskell or ML, you would get non-termination. But here it just works. So this shows that you can work with cyclic data structures really nicely in this language. And at the same time, we're able to avoid things like imperative programming, right? So the alternative to doing this in other languages might be to use something like a state monad to keep track of the nodes you've already visited. This gives us a nice declarative, purely functional implementation of these algorithms for cyclic data. And yeah, my takeaway from that is just that we've always sort of kept sort of like Haskell-like languages and and data-like languages in two separate bins. But really, they belong together. They are two sides of the same coin. Datalog is purely functional programming, and it's useful in tandem with the kinds of things that we typically think about as functional programming. All right, so now that we've learned sort of the basics of Granite and how it works, I want to talk about an application that we're excited about, which is modeling distributed systems. What's the hard thing about distributed programming? Well, there's a lot of hard things, but one hard thing is that we have to replicate data. We're running data across a network, and we want to make sure that it's fault tolerant. So in order to do that, we have to run the same program with copies of the same data on many different machines across the network. But when you do that, it turns out it's very easy for these machines to get out of sync with each other. So differences in just how messages are delivered might mean that a certain update gets to one machine very early on, and it doesn't get to another machine until quite a bit later. So how can we possibly program in this world where there's no single source of truth? Well, there's a couple options. One, you might try to implement something like Paxos with some consensus protocol where there's a lot of coordination performed, and that makes sure that the replicas are sort of always in sync with each other before you really try to do anything interesting. And sometimes you do have to do that. Sometimes it is necessary to write the program you want, but we don't want to do that if we can avoid it because it's very slow. And in practice, most of the time, or a lot of the time at least, we can avoid it. And instead what we do is we accept that these replicas are going to be out of sync with each other. And instead, what we try to do is, we just program up to the constraint that they eventually need to be the same thing. Sort of once all of the updates come in at the end of the day, they should eventually all agree on whatever value they're computing. This is a lot faster. And generally, it's good enough in most circumstances. But here's the tricky thing. What work do the programmers have to do to make sure that their program is eventually consistent and doesn't do any coordination? What do we have to, can we check that for them automatically? Do they have to do extra work? Here, it turns out there's a really beautiful result from the distributed systems world. It's called the Calm theorem, and it says that a program has a consistent and coordination-free implementation if and only if it's monotonic. That's really cool. Right, so here monotonic means that the program, as it gets more input, is only ever going to increase the output. It's never going to change its mind. If it gets some of its input, and then it says, oh, 3 is in my output set, it's never going to change its mind about and say, oh no, actually 3 wasn't in my output. It's always going to be consistent with that initial statement. Here, so here the Calm theorem, what it's doing is it's taking a consistency model, and it's reframing it as an algebraic property. And I like that because I'm a programming language researcher, and I know a bit about these algebraic properties, and I don't know a lot about consistency models. I don't like having to think about sort of when messages are coming in and all of that. It's just easier to think in terms of the algebraic properties. And monotonicity, in particular, is a property that we see all the time and is very familiar. And in fact, it's so familiar, there are certain things I think about when I think about monotonicity. And these are some of them. One is that Dana Scott told us a precise sense in which all programs in the lambda calculus are monotonic. And we've made sure that this is also true in Granite. So it seems like if Calm is telling us that monotonicity is eventual consistency, then it should mean that all programs in the lambda calculus are eventually consistent. It's not a very interesting statement because the lambda calculus is sequential and there's only one node, so it's not a very interesting system. But in Granite, we have parallelism that allows us to express sort of many nodes in the system, and it is useful to have this guarantee. The second thing I think about when I hear monotonicity is about fixed points. Oftentimes, we're guaranteed that a fixed point exists if the operator is monotonic. So the question is, then can we write a distributed system sort of as a fixed point of a monotone operator? Of course, I ask the question because this is the answer. We can model a distributed system in Granite through a definition that looks like this. We have n nodes, and we are calling each node here f of I. And each node takes in sort of the past state of the entire system, and it produces its sort of new local state that is computed based on the past global state. Now, the state of the whole system is the join of all the current local states of each individual node. And to get things started off, we can also sort of provide an initial state at the beginning. So this is sort of the form that the programs will take. We'll now take a look at a specific example. Oh, but I just want to point out that the programming in Granite sort of happens on analogy here, right? In a distributed system, if consistency is the thing you want, then the sort of corresponding PL concept here is monotonicity. Executing a distributed program is kind of like performing fixed point iteration in sort of programming language semantics world. And quiescence, the idea that like at the end of the day, eventually, after everything's been delivered, all of the nodes in the system agree on a value, is just like reaching a fixed point at the end of the fixed point iteration. So you don't have to read this code just yet. We're going to use a sort of simplified bookseller example that pops up in distributed programming a lot. The idea here is that there's two nodes in this system. There's a buyer node and a seller node. The buyer node is going to request to buy a particular book. The seller is going to respond with the price of that book. It has a database that's going to look it up in. And then the buyer will get the price and confirm that it wants to buy the book if it has enough money to do so. So now we'll step through. Sort of at iteration 0, we declared by fiat that the value of the system is going to be bottom. At iteration n equals 1, we've decided to just start with the empty initial state, which is undefined. And at this point, the buyer and the seller have not been able to even run. But in the next iteration, they start to be being able to actually do things here. So the buyer is now receiving undefined, which is the previous global state, as its input. And right now, all it can do is return the request for the book that it wants. So at this point, the buyer state is sort of request equals book 3, and that's also the state of the whole system. And now in the next iteration, the seller is going to be able to see this. So the seller now is able to see the request that the buyer sent, and it is going to formulate a response by looking up the price of the book in its database. And now in the next iteration, the buyer can see the seller's response, and it can check to see if the price is within its budget, and if it is, then it confirms that it wants to buy the book. And at that point, we've reached a fixed point. So this is a summary of what just happened. We see sort of the buyer state, the seller state, and the whole system state. And maybe the one interesting thing to note is if you sort of look from top to bottom along any individual column, everything is always monotonically increasing. That's sort of the monotonicity property at work here. So that was a really simple example. We're only at the beginning of sort of learning what kinds of abstractions and how we can sort of program these kinds of systems in a language like Granite. But the things that excite me are, one, we just defined a distributed system in a declarative, purely functional way that doesn't involve any mutable state or message passing, right? Oftentimes, these things are thought of as being very core to a distributed system. And I think the thing to take away here is that they really are just implementation details. They're important ones, but if you're going to specify the system, they're not directly necessary for that purpose. Number 2, there's no explicit notion of time available to the programmer. There is we saw in the implementation of Granite, there is sort of an iteration number going on here, but it's not something that the programmer ever particularly has to worry about or even has access to at all. Number 3, this is a global description of an entire system. So it's not just sort of one program per node. You can write an entire system as a program. Now you can split that program up any way you want. So if you want to only focus on the buyer and only focus on the seller, you can put those in separate modules if you want. But you have the ability to describe the system as a whole. And then the last 2 points we've talked about already quite a bit, which are you get this eventual consistency just by construction, as every Granite program does. And finally, coordination freedom. The only coordination that happened here was the coordination that the programmers decided to do, which was waiting for one node to send a message and then replying to that message. But there was nothing introduced by the runtime system itself. Everything was explicitly done by the programmer. One of the reasons that I think there's a lot of promise here is that there's been a lot of work actually on very similar languages in the past that are based on data log. And they've shown that this declarative programming approach to networking and distributed systems is really promising. And they even have results that have relatively simple implementations of protocols like Paxos, which are really complicated to implement yourself if you don't have this power of declarative programming. But we're able to implement this, we're able to integrate this declarative programming aspect into a fully featured functional programming language. So now you have a Turing-complete language where you're able to work with these, and you have all the abstractions and power that you get from the lambda calculus, higher order functions, all of that. And lastly, there's not that much for functional programmers to learn here. There's only this one new feature of join, and maybe sort of a different way of thinking about recursion. They actually have to think about least fixed points here, and not just sort of a more operational view that they might be used to. And we also think we can come up with a very nice sort of small core calculus to describe what's going on here. So just to sort of give you a heads up about what's going on right now, I am working on a non-deterministic small step operational semantics. We're building a semantic model in Iris, and we're going to use that model to prove out an equational theory. All of this being mechanized in Coq. We're using the Iris-based logic. And then I'm also working on a Granite interpreter that's written in Haskell. And something that we haven't formalized yet, but has sort of been a guiding principle, is that there should be a very nice denotational semantics here, which is sort of in CPOs, and it should be fully abstract, because you can write parallel programs like parallel OR. All right, so to close up, Granite is a declarative functional program with cyclic data. It's built for modularity and extensibility, and it enables distributed programming with eventual consistency by construction. All of these things seem kind of disparate, like why are they all in the same language? Well, they're all described by the same mathematical foundation, which is semilattices. Thanks.
Right, even before asking any questions, there's a question here.
Alan Jeffrey from Roblox. Very nice talk. So I'm wondering about the space usage of this implementation. In particular, it seems like in order to know whether you're contributing new data to this fixed point that you're approximating, how do I know that without knowing all the messages I've ever sent in the past? Because the obvious implementation is I calculate a new message to send, and then I only send it if I've not sent it again, because that's necessary in order to reach quiescence. So I'm just wondering how you implement this without unbounded memory.
You don't need like a log of all the messages ever sent. You do need the current state of the system or of the current node, right? You need in order to be able to calculate whether a fixed point has been reached.
All right, I'll take the question offline.
Okay.
Could you clarify your mutual recursive example? It wasn't clear how you determine which functions line up with which other functions when you do a join.
So we're talking about the extensibility example. This example?
Yeah. So in that case, you don't have mutual recursion.
Yeah.
But if the underlying functions were mutually recursive, when you do the join, how do you know which functions being called should be joined?
Yeah, so in order to do this, we have we encode a form of module, and each function in the module is named, and that name is not alpha vary, right? It's like a global name. So you merge it works just like records. I showed how records sort of merge based on when their fields are in common. You merge those the corresponding fields, and so the same kind of thing happens here. Functions with the same name got merged.
All right. I'm coming to the other side. Okay.
Hi, very nice. I think 2 or 3 slides before, when you showed the transitive closure of the graph, you showed this table of previous calls to f. And yeah, and in that case, the argument to f is unit, and therefore all recursive calls seems to be related. But what if f's argument is not the unit type, or rather something else? Does it mean you're memorizing all function calls in the past to recognize these recursions?
That's one implementation. But you can do better if you realize that for some of these functions, you don't need to memorize them.
So there would be no static optimization you do before and to see what's happening?
You could do it I was thinking dynamically, but
okay.
Yeah.
Okay, but I guess you could turn this into a selling point and saying, hey, it even has memorization built in.
Yeah, I mean, it does have, I don't know I think you want to be able to control where memorization happens. And so you need to do memorization at certain points to, in order to compute these fixed points, but you don't need to do it everywhere if you don't want to.
Okay, thanks.
Question here.
Yeah, so in your bookshop example, you use the iterations of the fixed point to sort of get kind of the rounds of a distributed algorithm. Your language, though, it includes like nested fixed points. So does that mean like within each round you have another nested computation that has to reach quiescence before you move to the next round?
Yeah, I believe that's possible.
Okay.
Still a question here? Yeah. I'll come back.
So I think one of your slides kind of answered the question, but how would you compare your language with a more dialogue-based language? So in a dialogue-based language, you have benefits like you get open recursion for free. You get modularity for free because like if you want to add more functions, you just add more rows, right? And so how would you compare the language?
Well, I mean, there are a few deltas between this language and something like Datalog. One is just the work that was done in Datafun, which is just adding lambda, right? You don't have first-class higher-order functions in Datalog. And we take another step from there in allowing sort of typical full general recursive functions.
I think we just take the two last questions here.
So I'm confused about something right at the beginning. You had this parallel OR, but you also have general fixed point, general recursion and undefinedness. And the parallel OR gives you problems with that. You have continuity problems with that. So what's going on there?
Yeah, okay. There's something kind of tricky going on here in that we said that this join operator is angelic, so it should succeed even if one side fails. Of course, one side failing might mean looping forever. So does that mean that you have to sort of detect if one side doesn't, is non-terminating? Because that seems like a computability problem. And there are a couple. The answer to this question is long. I guess the short answer is that there are two views that I take. One is that maybe the implementation I'm actually building only sort of computes an approximation. So it accepts that sometimes this program is going to diverge, even though the semantics say in an ideal world, the program shouldn't diverge because we just couldn't sort of detect that something was diverging. And that's, I think, still okay because we can still handle a lot of important examples here. But there's another view at which the semantics really do lie in with sort of the operation, but it requires you to take a little bit different perspective. And that perspective is sort of viewing programs not as these things that run and then terminate, but that as sort of streams that incrementally produce answers monotonically over time. So in other words, if you're willing to give up the ability to ask, has this program terminated, then you can sort of, you can get a nice implementation here that lines up with the semantics. If that doesn't make sense, I can explain more offline.
All right, one last question here. You want to take it? No, okay, we skip that one. Thank you. Let's thank the speaker.